Hi everyone. I'm going to present you a bit different talk from the previous speakers, because I will be speaking as engineer to engineers. Like this stuff that I present is published in scientific papers with all my co-authors, which I thank you a lot. But I would not go into prove anything or something. I would just explain what is image matching, how it's useful, and what are the good ways to do it. And I hope that at least some of this stuff you probably not know yet, because it's not widely known. Okay, so what's image matching is one of the basic computer vision tasks. Usually it's kind of not and user task. It's kind of a very useful instrument. So it's very simple. If you have two images depicting the same scene or same object, and you want to find correspondences between pixels, and more specifically, I am talking about wide baseline stereo, which means that these images are separated by large viewpoint change, or illumination change, or time change and occlusions, or even sensor change, when you have infrared versus visible. And you want to find correspondence. Why would you want to do this? This is workhorse for several end-user algorithms. One of them is 3D model. If you want to build 3D model out of video or collection of data, you will need image matching. If you want to do SLAM, you kind of try to do this end-to-end deep learning stuff, but so far it doesn't work that well. So this is popular ORP SLAM, and this is SuperPoint SLAM from Magic Leap. They tried end-to-end stuff, and they just then stick to learned image matching. Also, it is very useful still in image retrieval. Before, to whole image retrieval, when you have some image, say with I don't know, Eiffel Tower, and then you want to find another images with Eiffel Tower in your dataset, and it's not just labeled, you have just a bunch of images. So before it was just based fully on image matching. Now it's kind of it's just one step. This is winning Kaggle's solution in Google Retrieval Landmark Challenge this year, but this is still has this place. Okay, so what I am not be speaking about is first finding semantic correspondences. So this is quite separate, another type of problem. If you have eyes of cat versus lion, or another cat, or this goose, or the bicycle, is just another thing, which I don't know much about. Also, I would not speak about short baseline stereo. It would be covered by Anastasia later, and I would not cover the optimization for the stereo, because it was covered. It was covered in last years, and also mentioned by Bogdan. So there are already a lot of talks about this. Now, here is the typical pipeline. How do you want? How do you do the correspondence search? So you have two images, and you apply detector local feature to detect some key points. Would it be some windows or corners or blobs or whatever? Then you somehow select measurement region. Then you maybe want to normalize it to have better performance. Meaning if you have rotated images, so you maybe want to do some canonical orientation, or you want to deform your shape. Then you do descriptor, which is basically you convert somehow the image patch to the vector of float or binary numbers. And then you do matching, which is you just calculate distance between two descriptors or more, and take a guy which has minimum distance, probably is the match. Then you do, because it's kind of noisy process, then you do some geometrical verification if you have some model of what do you expect to see in the scene, would it be planar scene or whatever. So now I will go step by step or all the steps and like see how people usually do this and how one can improve it. And I will start from the end. And here is, I will spend some time here just to explain what's going on. So this is a very toy example. Like you have like, you have this image of dog man, and you have the same like graffiti from the very side view, and you want to find correspondences and or you like camera pose difference. So you detect features and describe them. You match them, you run ransack, and you draw results. So this is how it would look like for if you have done a good job. So let me explain what's here. So because this scene is plane, mostly, we want to match one plane to another plane, and in the dataset there is this green stuff. This is how image 1 is projected to image 2. And so this is like ground truth by like dataset providers. This blue thing, I don't know if you see them well, but it is very, very close to it, so we kind of find maybe good enough model, and yellow ones are correspondences which are consistent with our found geometrical model. It's important they are consistent with found, not with the ground truth. They consistent with ground truth only if like found and ground truth coincide. So let's go. Ransack. First, what are kind of typical geometrical models of the scene which you can use? Like one of the most common and like a very good one is homography, which means like if you have planar scene or you have like static camera which only do zoom and or rotation but don't move, so you can safely use homography. You need to just for correspondence to find it, and what is good is this kind of one-to-one, so you can reproject with this pixel from here to here and back. So this is how it looks like. Another model, if you're like very 3D, if you're photographing a statue, which is like obviously not planar, then you would go for a more general model, which is epipolar geometry. Epipolar geometry describes how the point projects to the image plane of camera, and so this point is projected here, and so fundamental matrix is connects this point to that line, which means that we don't know the depth, and because this actually can be any of these points, so what we know for sure that this point should lie on this line in image 2. So it's weaker constraint, and we cannot use like bijection projection here. And it's like still a rigid scene. For example, if you're photo traffic, you have a lot of cars which is moving, this is like not enough. But like for most of cases, for example, for 3D construction or SLAM, it's kind of sufficient enough model. Oh, and these are two models which are implemented in OpenCV now. The last component, and so like how to find these models, would it be epipolar geometry or homography? There is a popular algorithm for this, ransack, which is like robust. This is random sample conception, and it needs to be done because of the outliers. So you have your observations, a lot of them are correct, but a lot of them are not correct. If you just have like least squares, you fit and you would get this red line. This is not what you want to do. So instead, you sample the minimum number of points to find your model. For line it's 2, for homography it's 4, for fundamental matrix it's like 7. And then you draw this line, and then you, in the neighborhood of this line, you calculate number of data points which are consistent with it, and like you pick the model which is have best number of points associated. This is like very old, well, not very old, it's like from 80s algorithm, and this is also is implemented in OpenCV. Now let's try to do this. So we have OpenCV runtag for finding homography and our CMP runtag. CMP is our lab which I work. And you see this is kind of very wrong. And this is what you have like with dirty correspondence out of the box, even with all this optimization, doesn't work that well. Why? If you look, so you can see here 1, 1, and 1. So this is line, and this is group of correspondences, which is consistent with like because they lie nearby and they correspond to the very almost same point. So if you have a group of points in the same position or nearby, then you will be consistent with any model. So, and how to fix this? It's a very simple thing. You calculate your error in 2 ways, because usually what's done, homography is from image 1 to image 2, and not other way around. If we just want to check if our correspondences are also consistent with a given error to another way, so then we'll find very, very simple, like very, very fast and like correct model. And this is how to implement this. And you don't need to implement this. Like, we will release like Python package with like our runtag soon, so stay tuned. And this is also shows like, this is kind of not thing which you would get published, but this you actually care if you do this in practice. So everyone use OpenCV, you run OpenCV, and here is a problem. Okay, here is the solution. Now let's continue. If you have like more 3D, you cannot do that, so you use fundamental metrics. And because of like fundamental metrics matches the point to a line, so these correspondences are not correct, but like your model cannot tell you this because all the correspondences on a particular line here would be correct because you don't know depth. So what you can do to fix this? You can remember that when you detect local features, they are typically called key points, but they are not key points, they are regions. Like for the SIFT, they are circular oriented regions, or for others it can be ellipses or whatever, and you can have like more points. So you first fit the model with the like centers only, and then you check if these points actually points on the like circle, so from the region if they also consistent with the model, and you can see that here they are and here they not, despite the correspondence is actually correct, but so the detected orientation is not. So, and if we apply this kind of check, then this model would be rejected because of like low inlier numbers, and then model will find this one. So again, very simple thing. It's implemented in our runtag, and this is like what you probably should do when you run the stuff practically. Now, matching. Very, very simple thing, but also can have problems. Let's start with the basics. Here are descriptors from image 1, here are descriptors from image 2. This is like descriptor space, so this is just to example. For each descriptor here, we find nearest neighbors there. And you can already see the problem. First, the problem is that you can have many to one correspondences. And second, you actually, maybe it's coincidence that this corresponds to this, not to this, like, because they are like really, really close. But so like nobody in probably like classical computer vision uses this stuff, but then deep networks come, people don't attend the courses on like classical computer vision, and they use this stuff. Now you have this problem, and yes, I kind of cheated in the sense that I used classical OpenCV runtag without my tune before, but I need to show you what the problem is. So now, What if we want to have like more strict condition? Is that we want cross consistency? That if this guy is best friend with this, and this should be best friend with this. So now we have like less correspondences, and they are kind of more hopefully precise. Still not enough. Now here is kind of, it was gold standard for many years until it was neglected in CNN era. So you can do like a thing that you retrieve not one correspondence, like a nearest neighbor, but two. And then you compare the ratio of like distance from first to second. If first is kind of close, much closer than second, then probably it's a good match, like reliable. And if they're very similar, this is probably something like random. And here is, it was proposed by David Lovett in his SIFT paper. And here is a graph from here. So this is probability distribution empirical for the correct correspondences. Here is ratio, and this is percent of features, sorry, correspondences. And this is for incorrect. So if we keep some threshold like between here, then we will get the most of correct ones and filter out the most of incorrect ones. So it works. Now, sometimes, like if you detect really many features, you can shoot yourself in leg because, for example, you can have multiple orientation in the same feature on the symmetric objects, and that's why your second nearest neighbor, showed in red, and correct first neighbor is in green, they are actually very close here. And of course the descriptors are also close. You have bad ratio, but and you filter out these correspondences, but they are good. So what we can do, we can say, okay, we would like to find second nearest neighbor from some which is far enough from first neighbor to be kind of inconsistent with like geometrical model, because otherwise it doesn't matter if it corresponds to this or to this feature. So, and this is, we call this first geometrically inconsistent nearest neighbor, and these are yellow guys. Now, what? So it shows something similar, but to previous. But if you compare, you can see that our geometric model recovered. This blue is closer to green than previous one. So we have more correspondences and like better model. Now, what you can do next? This is like still a symmetrical process. Like if you have 1 million features here and 2 features there, you would have 1 million correspondences, like kind of. So what, how you can do this symmetric? So you do matching both ways, and then you somehow combine the outputs. If you need more correspondence, you just concatenate everything. If you need like less but like more precise correspondence, more reliable, you then keep cross-consistent one. And well, I think which you can do, you can use deep learning magic. So this is like you have X and Y correspondence, or X and Y coordinates from image 1, image 2, and you train some black magic neural networks to output like confidence scores. And there was oral presentation on CVPR. So let's check how it works. Unfortunately, I don't have the thing for my toy example, but I have something better. This year at CVPR there was image matching workshop and challenge. So people submit their cool features and like matching methods, and organizers run. Organizers run ransack, estimate the camera pose difference between like 2 images, and then compare these to ground truth pose difference, and basically calculated number of precise enough camera pose recovered. More specific, it's MAP at 15 degrees error. And okay, so nearest neighbor is this one, perform very poorly, and this is like combination for different detector and descriptor. So this is classical SIFT, this is SIFT plus deep descriptor, another deep descriptor, and like fully learned stuff. And you see that this gold standard works quite well. For geometrically inconsistent variance works better. And this guy is winner of competition because we haven't submitted this green stuff. It was done like after the competition. And you can see that actually that very simple heuristic for field geometrically inconsistent neighbor works much better. Well, not much, but better, and much faster than all this deep learning magic. So it's not the always good thing to do to train deep network. And like takeaway, so use this field geometric inconsistent. It's like really cheap and it gives you improvement like right now. Now we will use some deep learning, but for training descriptor. This is joint work with Anastasia, and this is we're like lucky enough to become kind of standard deep learning descriptor for a while with it. So how to select good correspondence? You already know this. So you first find the nearest neighbor, and then you filter out bad ones with this first to second nearest neighbor ratio. So let's use this to train neural network. Here is an architecture. This is like very simple VGG style. You have convolution, ReLU, and match norms, nothing more. And here, what network is optimized for? You sample pairs of positive patches, which correspond to the same like 3D point from dataset. And you want that descriptor distance between positives should be small, and between positive and any of negatives should be large. So it's done with optimizing triplet margin criteria. So this is like margin plus positive distance minus negative distance. And before people do when use triplets, they usually sample actually negatives randomly. But this is bad for two reasons. First, like if you randomly sample some negative patch, it probably would be like not similar enough to provide you like useful information, useful gradient. And second, you actually need to run your CNN like 3 times for this batch, for this batch, and for third. So instead, we can run it only 2 times, and then calculate descriptor distance from all to all, and then keep just the hardest negative in the batch. And this is also better than also classical hard negative mining through all the dataset, because it's stochastic, and if your dataset have like bad labels, when your negative is actually mislabeled positive, you will, like, if you go through all the dataset, you will definitely find them and use them for training, nothing good. And here it's like quite unlikely that you will pick these things in the single batch. So this is how it helps, like almost 2 times. Now, at the time of publication, it was state of the art. Then we tuned hyperparameters a bit, and we got like much. Again, maybe not too much, but in this benchmark, it's much better performance just by tuning hyperparameters. And more importantly, that this like architecture and the training scheme, it scales with bigger datasets. So, Indian guys, they gathered a huge data set called photoscenes and trained hardnet on it. And they have some numbers. Another guys from Singapore, they gathered another huge data set. They designed new sampling method, like complicated loss functions. And if you just compare, that it's actually almost the same. So like vanilla hardnet scales with more data like quite nicely. Now, on Facebook, I ask it like, what would you like to hear about? And one of the guys said, well, nobody tells how to prepare a dataset. So please tell about this, and I will. So there are like existing datasets for training local descriptors, so it's like not just to see now, it's links, and if you download slides, you can click and go. But the problems with most of them that they usually have a huge viewpoint change for training, but not that much illumination change. Like if you want to match day versus evening or night, it's not much data. So we pick the AMOS dataset, which is like terribly huge dataset with like 10 terabytes. This is like collection of public web cameras, like 30K, and like for many years, and like every minute or every hour, depends on camera, as they save an image. We actually stopped downloading on 10 terabytes because we were out of space. And we first said, okay, let's train on this huge data set. But it turns out that it's not that easy. Some cameras are really, really good, but some are blurred, not working, or depicting the like very dynamic scene. And our kind of idea and motivation to use the dataset is that, okay, if the camera is static, you probably already know all the correspondences, like that these pixels here and like in 1 hour should correspond to the same object. So we need to filter. And so here is like complex process, and sadly from almost 20K we go to 50 cameras. But this was important to get some meaningful result, fortunately. So first, we have just a lot of simple empirical checks to reject cameras. So we randomly draw 20 images, check if the sky area is small enough. For doing this, we just run some out-of-the-box sky detector. It was working quite well. Then if it's like no cars on board, we again picked off-the-shelf detector, because if there are cars and boats, then it's like highly dynamic thing, we don't want this. Then if it's like sharp, if you don't want to train on like over-blurred stuff, if this is like camera is working, because it's you don't want to work with non-working camera, and if this is like higher resolution enough. So then we run like appearance clustering, because for each camera we have, if you think about it, like every minute, 24 hours, and probably like now and in 1 minute there would be not a difference in like image. You don't want to process and store basically duplicate data, so we just take the fastest thing to get an embedding. It's AlexNet. We run through, we cluster it, and we pick only like 120 like clusters in like single camera, so they are representatives of this camera. Now we match the images, because you know this AMOS code is like static cameras, but they are not. There is some wind, some also camera like just changing or rotating, so again it's not that easy as we thought. So we run a registration algorithm, we pick matching pairs, we get homography, and it's not, if it's not identity, we make like we warp an image to make an identity. So, but there is a problem if you run like sparse feature matching algorithm. Sometimes it just matches like some part of image, and you want to match whole image. That's why we use optimization algorithm, again out of the box in GDB ICP, so which iteratively optimizes the reprojection error and gets like your pixel to pixel correspondences. Finally, we still need to go manual, but it was not that hard now, because you can have dynamic scenes with cats, not with cars. Like, so some people just put like how some cats live, or you can have some cafe, or it somehow was not detected by sky detector, or it's just snow, or so. Go through, and finally we get these patches. Now, how important to clean your data? Maybe we did like a job which we haven't need to do. So this is like performance of your descriptor hardnet, and depending on how your data is like deregistered. So like if you have very deregistered data, your performance drops. So you need to have good registration. Also, it's also important how to like combine these images into the batches. Like, and if you have any metric learning algorithm, this is kind of universal thing that like usually some closest negative, so thing which is like good for training, goes from the same condition as your positives. So for us it was like closest negative for the patch also come from the same view of the same cameras. So if you have less views, like less cameras in the one batch, we have better performance. This is like just some numbers, and because we try, so this was before if you train and test on like illumination, and we got like quite nice improvement on illumination, but it's like not the major, but it's still nice and it's like working well, and it was the master project. Okay, now. Then, to describe something, you need to have this something, and this is you have some regions. If you have SIFTs, you have like circular points, but you can have an orientation or shape. So, regarding orientation, like a classical way how to do the orientation estimation for patches is just dominant gradient. You calculate gradients, and the dominant gradient orientation is like what you need. This is like key point, and then you normalize the patches to this. So you rotate, so you have original patches, and then you rotate to have this always vertical. Or you can again train CNN, and this is where it kind of works well. So. Or you can do nothing if you are sure that photographer is like a normal human who probably wants to just take a photo of something without like a horizon, not horizontally, and you just can skip the stage. And actually this which works the best, like going from like classic to learn to improve results a bit, but just throwing it away so you can have no error there, so it's much better. Now, what you also can do, if you have like large viewpoint difference, then you can like deform your region from circular to some elliptic one to kind of mimic the like camera movement or so on. So this was done before in Hessen affine detector in like 2002, and then people neglected this, so we revised this with CNN. And does it help? Yes. If you have like huge geometrical changes, then it gives you more inliers. How to train this? The same way as you train descriptor, but with spatial transformer. So you take two patches, you randomly deform them, you crop to fit in zone network input, then you output the geometrical transformation, then you put this into a spatial transformer, which is just like differentiable bilinear sampling of the pixels, and you deform this again, you describe it, and you want to again maximize distance to the like negative examples and minimize between positive examples. And now what I think is detector. It is like last but not the least, because it's actually main like thing which gives you failure. So there was a study on that, like similar to this AMOS dataset. So people take these cameras and then try to match the features from here to like plus months, plus 1 year image and so on. And so here is a graph. So this is like periodic, like summer, winter. But so successes are red, like descriptor failures are green, and the detector failures are blue. So like if you improve the descriptor, you can have like 2 times more correspondences. And actually this is almost exactly what you have with going from SIFT to learn descriptor. And the rest, to recover, you need to learn or craft some good detector. But the problem is that it's no yet a good practically working learned detector at all. So we still use stuff from 10, 20 years ago because it works the best. So let's review them. So because of OpenCV, people say, okay, here is like SIFT detector descriptor, I will use this. And this is like really annoys me because there is SIFT descriptor, but no such thing as SIFT detector. It is just simple difference of Gaussian, which is actually the very simple blob template. So you take this patch and you compare with every patch of the same size of image, and where there are such blobs, it fires. Good. Of course, this is kind of not optimal way to do. There are like more clever ways how to calculate this, not just template matching. So you first build image pyramid. So this is like image pyramid is gradually blurred and downscaled version of the image. And then you just have a difference of the nearby levels, which is like mathematically equivalent to run this, but much, much faster. So, and like this simple guy is still probably one of the most used and best detector in the world for local features. Another very good and popular is corner detector based on segment test. This is called FAST. And the idea is very simple. If you have corner, then probably it's like light or dark, this angle stuff, and this should be different from it. So if this is dark, then here should be light, or other way around. And you don't do this check of the pixels like sequentially, you do it in this way, so like to optimize to faster rejection of non-corners. And this works surprisingly well. Now, there are like jointly learned detectors and descriptors, which I am not going to describe in detail, but like I will mention some of them which have like some applications or success. So one is SuperPoint. They first have like CNN to output detector, like key point position and descriptor, and they train to first on corners and junctions on like synthetic data set, and then they fine tune this on real data. This is what is used in MagicLeap. This is like very fast. This is like better than fast detector, but kind of not that good as SIFT for some tasks. Delph is one thing which you probably should use if you do landmark recognition or retrieval, because it's like, again, deep detector which was trained on exactly landmarks. So this is some image, and this is like landmark part of the image. And the problem of running like conventional detectors like FAST or SIFT, that, for example, if you want to recognize some landmarks and you have a photo, and this photo have a grass or tree, you would have lots of features on the tree and grass because like lots of corners, but you have to filter them somehow. This is like way to like just concentrate on features which are on the. So. And third is like recent one, this CVPR D2Net. They actually combined all the like things which you would like to see from the detector. They formulated it mathematically and then just make neural network to optimize for this. It's kind of a good thing to do, but it's like not yet tested like in industry on practical tasks. And here on these two examples, so this is like SuperPoint, this is D2Net, and this is like still dog plus hardnet, and you see this is still not yet ready to replace this pure blob detector. Now, what if we combine all the things I mentioned together? This is like not naive, like this is like proper way how people do stuff, and this is how you do the stuff with everything I mentioned. So you see that you have much more correspondences and a bit better geometrical model. So, like very last thing to do is like if you desperately need to match the images which are like very viewpoint different, like you have from one side and from very other side, which is probably you can match this to this, but probably not this to this. What you can do, if you can do just basically test time augmentation, which means that you synthetically warp images and run your detector's descriptors on them, add like reproject features to the original image, try to match, and doing this kind of like iteratively, so that fast. And this is, thank you for attention. This is like recommendations in all together, and this is where I will publish the like code I promised. So this is kind of ready but not yet cleaned up. So I'm shy to publish the dirty code. Thank you for your attention and questions.
Thank you, Dmytro. Do you say you have 20K links in dataset, but you choose just 50? So it will work on blurred images?
Images of who? Sorry, what I don't get the question.
It will be work on blurred images because you trained without bad images in dataset.
Well, like, would it work on bad images? Is this a question?
On blurred images.
On blurred images? Okay. Yes and no. For like some amount of blur it would work because we killed only like completely blurred out images, but for images which are like very blurred it would not work, but not because of descriptor, but because you would not detect any points there. So it's kind of irrelevant because other stuff also would crash there. So.
Okay, and by similar images and zoomed images. So the descriptor can find zoomed details.
Well, descriptor don't do some. So zoom, which means the scale. Okay, so where I have some features here. Hopefully, okay. So the scale of the feature, and the feature would be detected at the same scale on like whatever image you have, like in if it's visible. This part is done by detector by detecting on scale pyramid. So you will always have almost the same region, and it doesn't matter how scale difference if you have in images.
Yeah, okay. What is the result by similar images? Similar but not the same.
What does it mean, similar but similar, not the same?
We have an image with Eiffel Tower and some similar tower, but not.
Hopefully it would not survive the geometric verification.
Okay, but if this is similar but not the same. In Kiev we have Alpha Tower, but not the same. So.
I mean, what is purpose of doing this? Like, it may be matched, it may be not. I don't know. Like, and if you want to do this specific task, you can probably add some more constraint. If you this model doesn't know about like world. It knows about this current image, and it knows only if this geometrically consistent this matches. That's all.
Okay. In the
and maybe this is the last question for me because other people also want.
Yes, last. Can you the graphs before?
Before?
Before, yes.
To what?
Loss function graphs for.
Loss function?
Yes.
Okay.
No. The before. Yes. This.
This one?
FGINN. More 3 people use this. Is this optimal way to make this task?
Guys, you will have time during the networking evening, so I believe you will have an opportunity to talk to Dmytro. Thank you for your questions. Yep, thank you.
Thank you for your talk. I will look for your code to test it. One first question, will you have a pre-trained weight for all this stuff published already with your model, the descriptors and feature structures? And the other one, have you considered using the synthetic dataset as was mentioned in the first lecture? I mean, to have the synthetic, real synthetic data. I mean, and use this with real data to get possibly better results.
Yes, but so far I haven't time to actually use so there is some work should be done to extract patches and correspondences, and I haven't done this. So it's engineering work needs to be done.
Okay, thanks.
Thank you for your talk. I would like to say that this CVPR, there was also, in addition to G2net, there was a paper called Detector retrieve. So basically, my question is the next one. What do you think? Is this? Have you read this? And is this a cure for the problem of combination of local and global descriptors for such kind of problem?
I think. Well, it's okay. There is a paper how to do mid-local features to do image retrieval. This is a good paper, but it's not the solution. I think it's just intermediate step, and
okay, we have time for 2 more questions. I have seen one more here.
Thanks for the call, for the talk, and the question is the following. You mentioned that this approach could work on different modalities, like visible images versus near-infrared, etc. And the question is how close these modalities should be. Is there any constraints or sufficient conditions to this approach to work? For instance, will it work on thermal and visible, or optical and radar?
Okay, for thermal and visible, well, it depends. It's kind of works out of the box on some images, but of course, if you have radar or thermal, probably you should create your own data set and train your descriptor there to have a decent performance. Because I would say that so this stuff is kind of, if you have infrared visible images, you can, I think from this data set we can match 20%, which is not bad because we haven't trained at all for the multi-sensor, but we can match some of them, but to use it in practice you need to train on it.
Which algorithm approach, by your opinion, is better for essential matrix calculation for geometrical filtration of matches? Which one you prefer? Thank you.
I usually don't work with essential metrics at all because I don't have camera parameters, so I cannot answer your question. Usually, like if I have camera parameters, that is kind of a bit different task, and this is solved by other guys. I just take images without them.
Okay, thank you for questions, and thank you, Dmytro.